NASA's Voyager 1 spacecraft, which currently holds the record for the most distant object ever built by humans, has captivated people globally for nearly 5 decades. Since its launch, Voyager 1 has transmitted vital data from the farthest reaches of outer space, improving human comprehension of the universe. However, the probe's recent transmissions have exhibited unusual anomalies that have left specialists perplexed. These enigmatic signals have ignited intense discussions, prompting the scientific community to question whether these irregularities are mere technical malfunctions or signs of something far more extraordinary, possibly even from another planet. Join us as we investigate these perplexing messages and explore what could be concealed in the vastness of the cosmos. The intrinsic human desire to solve mysteries has long fueled our quest for space exploration. This profound curiosity paved the way for ambitious projects such as Pioneer 10 and Pioneer 11, which were among the most courageous space missions of their time. On August 20, 1977, the launch of Voyager 2 from NASA's Kennedy Space Center marked the beginning of a revolutionary era in space research. Shortly thereafter, on September 5, 1977, Voyager 1 was dispatched into space, embarking on a journey that would lead it to the outer planets, significantly altering its trajectory and scientific outcomes. Each probe, the mass of approximately 721 kilograms, about the size of a small car, traveled in distinct directions at varying speeds. On December 15, 1977, a significant milestone was achieved when Voyager 1 surpassed its twin in terms of distance covered due to their divergent paths. Since then, Voyager 1 has served as a crucial asset in deepening our perception of space, contributing to discoveries that have transformed our understanding of the universe. Before delving into some of its recent revolutionary findings, let's revisit a number of its earlier key accomplishments. In 1979, positioned approximately 265 million kilometers from Earth, Voyager 1 captured high-resolution images of Jupiter. By January of that year, it had completed an impressive 100-hour study that produced a time-lapse sequence depicting the rotation of Jupiter. This set of 3,750 images provided unprecedented insights into the agitated atmosphere of the planet and its complex features. During this mission, Voyager 1 also detected a previously unidentified ring around Jupiter and discovered 2 unknown moons, significantly enhancing our knowledge of the gas giant's intricate system to maintain its course and avoid colliding with Titan, one of Saturn's moons. The probe performed several navigational adjustments. Subsequently, the mission shifted its focus beyond the solar system's planets, as the spacecraft was redirected into interstellar space, traveling at an extraordinary pace of 325 million kilometers per year. In January 1990, Voyager 1 commenced its assignment to explore interstellar space, moving beyond the boundaries of our solar system. During this phase, it accomplished a number of extraordinary feats, such as identifying 4 new moons, Mimas, Enceladus, Tethys, and capturing some of the most memorable images of the solar system's outer boundaries. On February 14, 1990, Voyager 1, located approximately 6 billion kilometers from the Sun, took the iconic family portrait, a panoramic collection of images of the inner planets. This compilation of 60 photographs was added to the probe's extensive gallery, which already featured hundreds of images from its close encounters with the gas giants. Voyager 2, in parallel, achieved remarkable milestones during its journey. It measured wind speeds on Neptune that topped 2,100 kilometers per hour, roughly 1,300 meters per second, the fastest atmospheric currents ever recorded in the solar system. It also observed Triton, the largest moon of Neptune, where temperatures plummeted to a frigid minus 391 degrees Fahrenheit, minus 235 degrees Celsius, ranking it among the coldest known locations. Triton's surface showed evidence of icy eruptions, spewing nitrogen, gas, and frozen Debris up to 5 kilometers high, revealing fascinating new aspects of its geology. These extraordinary discoveries significantly broadened our understanding of the diverse and dynamic conditions in the solar system's outer regions. The impact of both Voyager 1 and Voyager 2 has been truly transformative. Their findings unveiled previously concealed characteristics of Jupiter and Saturn's moons, once thought to be inactive. This new evidence redefined beliefs about their geological activity. In particular, Voyager 2 made history as the only spacecraft to date to pass close to both Uranus and Neptune, an unprecedented success. NASA used a series of innovative strategies to extend the lifespans of these groundbreaking missions, such as powering down unnecessary components to reduce energy expenditure. The undertaking is projected to continue until 2030, symbolizing the conclusion of a wonderful chapter for the dedicated mission teams. The construction of Voyager 1 and Voyager 2 exemplified advanced design and engineering. Built to rotate slowly, these probes minimized motion, blurring images taken while traveling. Even before reaching the other planets, the spacecraft began relaying detailed images of Jupiter, displaying its swirling clouds and the well-known Great Red Spot, a colossal storm that has piqued scientists' interest for decades. One of the most thrilling discoveries was the detection of volcanoes in active eruption on Jupiter's moon Io. The spacecraft encountered odd readings from the moon, later validated by images revealing massive volcanic plumes and a violently reshaped surface. One eruption on Io was found to be 1,000 times more forceful than Mount St. Helens, blanketing an area nearly the size of France. As their respective voyages continued, spacecraft systems were gradually powered down to save fuel. Strikingly, they did not capture images of Mercury or Mars due to technical constraints. NASA later launched additional noteworthy missions, including Pioneer 10, Pioneer 11, and New Horizons. On February 17, 1998, Pioneer 10 surpassed Pioneer 11 to become the most distant probe from Earth. Nevertheless, Voyager 1 continued its journey for another 14 years before officially penetrating interstellar space on August 25, 2012. A pivotal factor in the success of these missions was the deliberate application of gravitational slingshot maneuvers, which accelerated the spacecraft toward their objectives while conserving fuel. Rather than depending entirely on propulsion systems, they harnessed planetary gravity to gain velocity and alter their courses. This technique enabled them to span colossal distances with minimal fuel expenditure. As Voyager 1 approached Jupiter, the planet's immense gravity accelerated the spacecraft. Precision was essential to avoid hazardous changes in speed or trajectory. These gravitational boosts allowed the probes to expertly traverse the solar system. Voyager 2, likewise, exploited gravitational pulls from Jupiter and Saturn to propel itself toward Uranus and Neptune, validating the efficiency of this extraordinary interplanetary strategy. Navigation method, reflecting on these extraordinary initiatives taken by the scientific community. The world eagerly awaits additional information from the anomalous transmissions recently detected by Voyager 1. These spacecraft continue working well beyond the solar system's established perimeter, probing the mysteries of planets like Jupiter. The Voyager 1's observations of Neptune, Saturn, and Uranus vividly documented time-lapse sequences of eruptions on Jupiter and revealed new satellites, as well as a previously unidentified ring that surrounds the planet. These revelations significantly enriched our understanding of the Jovian system. Similarly to Voyager 1, 4 additional moons orbiting Saturn were discovered: Mimas, Enceladus, Tethys, and Rhea, while also providing breathtaking visuals of the planet and its rings, illuminating their elaborate structures. The mission's expeditions to Neptune and Uranus yielded critical observations about their atmospheres and satellites, enhancing our grasp of the solar system's distant territories. After finishing their planetary flybys, both probes set course for interstellar space, where they persist in collecting crucial scientific data. This ongoing investigation widens our perspective on what exists beyond our solar neighborhood, as we await new developments pertaining to Voyager 1's peculiar emissions and their repercussions for our comprehension of the incredible journeys of the cosmos. These probes continue to inspire both researchers and enthusiasts globally. Their accomplishments remain foundational in expanding human knowledge and pushing the limits of space exploration. Voyager's programs have delivered unprecedented glimpses of our solar system in regions far beyond, offering iconic imagery and valuable scientific results, in addition to their actual contributions. The spacecraft convey a message with a symbol, crafted to represent Earth to potential extraterrestrial civilizations. The golden record contains greetings in 55 languages, musical pieces from various cultures, and natural sounds like thunder and whale songs. This interstellar communique serves as humanity's hopeful attempt to communicate with intelligent life in the universe beyond Earth. Voyager 1 and 2 were outfitted with an array of scientific instruments that significantly enhanced our comprehension of space. For example, magnetometers, plasma wave sensors, and imaging equipment, each of which provided critical data about space environments. The magnetometers helped unravel the magnetic fields of Jupiter, Uranus, Saturn, and Neptune, revealing how these fields interact with their surroundings. Plasma wave detectors clarified the influence of solar winds on planetary MOS. A TMOSPHERS. One of the mission's standout achievements was tracing the line that separated the heliosphere, vast region populated by solar particles and electromagnetic fields that envelopes our solar system. As Voyager 1 approached this boundary, it witnessed a shift from solar wind to interstellar material, yielding essential insights into how this barrier protects the spacecraft and Earth from cosmic. Reza also pinpointed a location called the termination shock, where solar winds decelerate and condense. Beyond that lies the heliosheath, a turbulent region where solar and interstellar particles collide, creating a dynamic environment. Voyager 2's expedition also greatly enhanced our comprehension of the outer solar system. Close encounters with the enormous planets provided crucial information, especially regarding Uranus's magnetic field, which was found to be inclined in an unexpected manner that defied existing theories. These findings have prompted additional research into planetary magnetism. These endeavors not only advanced scientific understanding, but also rekindled the public's interest in space exploration. The mesmerizing images of far-off planets and the enthralling stories behind these missions have inspired countless individuals across generations. Iconic visuals like Saturn's rings, Jupiter's volcanic moon, and other elegant moons have become emblematic, encouraging new scientists and aspiring explorers. As the Voyager spacecraft persist in transmitting exceptional information, their prolonged exploration of interstellar realms offers unmatched opportunities to decipher the fundamental nature of the universe. Although prior emphasis was often placed on the planets of our solar system, delving into interstellar regions has revealed surprisingly complex zones. Once thought to be empty, these areas are now known to exhibit intricate phenomena that challenge current scientific paradigms. Among the most captivating findings is the detection of cosmic rays originating from beyond our solar system. These highly energized particles, traveling nearly at the speed of light, provide hints about the processes going on in remote parts of the galaxy. By examining their energy levels and composition, scientists aim to better comprehend the dynamics of stellar nurseries and galactic behavior. Moreover, Voyager 1 and 2 delve deeper into interstellar space. Their instruments continue to evaluate the interstellar medium's density and motion. This diffuse matter composed of gas and dust occupies the space between stars and interacts with the solar wind, shaping the heliosphere's configuration. During the probe's movement through this medium, they relay invaluable information, That assists researchers in modeling the operation of matter and energy over great distances in the cosmos. These contributions have unveiled essential details about magnetic fields in the space between stars, shedding light on their properties and influence. These revelations could eventually drive breakthroughs in understanding magnetic forces throughout the galaxy. The ongoing exploration of these distant frontiers not only extends our scientific awareness, but also inspires future generations of space enthusiasts, scientists, and engineers. The unforgettable images obtained by Voyager, especially the renowned pale blue dot, depicting Earth from more than 6 billion kilometers away, serve as a humbling illustration of our tiny presence in the cosmos. These photographs, combined with the mission's scientific accomplishments, have deeply reshaped how we perceive our world and its position in the universe. The success of the Voyager missions has paved the way for even more ambitious ventures. Thanks to the advancements developed during their journeys, launching sophisticated probes to more remote corners of the galaxy is increasingly attainable. Goals such as traveling to exoplanets, identifying potentially habitable worlds, and even interstellar travel are steadily evolving from visionary concepts into practical objectives for the future of cosmic discovery.